Good afternoon, everyone, and welcome to today's broadcast. In the next 40 minutes or so, I would like to share with you some of the results that we have recently published. And these results were, obtained from our nano-satellite that's currently orbiting in space. Now, the nano-satellite we call SpooQy-1 was deployed from the International Space Station in June last year. And you can see in this picture over here, the astronauts actually took this very dramatic picture as the satellite was leaving this deployment mechanism that's attached to the space station. And one of the nice things about these photographs that they take of the satellites as they leave is that you can, frame, the size of the satellite with respect to the space station. And you actually see how small it is. Now, in this talk, I will not only just share with you the results that we have obtained, but also talk to you through some of the work that the team has been doing over the last few years in order to prepare the instrument for operation in space. And I will conclude by saying a few words about what we can look forward to in the future. Now, for those of you who are not from the CQT, I lead a small research team that we call the SpooQy Action team. And what we do is we concentrate on developing entanglement technology for communications. In this picture, what you're seeing is the SpooQy team that's associated with the satellite. And we took this picture, just before we had shipped the satellite to Japan for integration, so that it was ready for launch from this space station. And you can see Rob Baddington over here is holding up a model of the SpooQy-1 satellite, and we're standing next to a Yagi antenna with which we can control the satellite as it flies over Singapore. And this is on the rooftop of one of the buildings at the Faculty of Science. Now, for those of you who are not physicists, you're probably wondering what is this SpooQy action and why do we keep making use of this term spooky. It's actually a phrase that Einstein used when he was talking to his friend via letter about one of the strange properties of quantum physics, which is known as entanglement. Now, when you have entanglement between two physical systems, for example, between two photons, they share very strong correlations. And these correlations would exist over very long distances. And if you were to make measurements on one of these photons, you could make statements about how the other photon would actually behave, although it's very far away. And if you try to describe this sort of behavior using physical intuition and based on an understanding of classical physics, it is actually quite disturbing. It is actually quite mysterious, and you can't really explain how it is actually possible. And this disturbed quite a lot of the original founders of quantum physics, including Einstein. And so he called this SpooQy action at a distance. Of course, nowadays, we understand entanglement properties a lot better. And we also understand that you cannot get superluminal communication using entanglement. However, you can still use it for interesting applications. For example, if you had entangled photons and you could distribute them over long distances, you can use those correlations for quantum key distribution, or QKD, or you can try and use them for teleportation, or try and use them for authentication. At the same time, if you have entanglement, you can use them to connect quantum computers that are quite far apart. And so sometimes we think of entanglement distribution as one of the requirements if we were to build up a quantum internet. And of course, if we have a quantum internet, we would like to have this on a global scale, just as we have an internet today that's over the global scale. And of course, at the same time, entanglement applications are just emerging, and there's a lot of work right now trying to see how they can actually be used to improve timekeeping or to improve sensor networks. And that's one of the main reasons why there's a number of groups around the world trying to study how entanglement can be distributed efficiently around the world. Now, the main problem that we all face is that of range. you can distribute entangled photons over optical fiber, and we've done that also in Singapore. But the main problem is that you see losses, and typically in deployed fiber, your loss will be about minus 0.3 dB per kilometer. And so if you have several hundred kilometers of fiber, you would have already a lot of loss. For example, over here, we talk about minus 80 dB loss for 270 kilometers. And this is actually a real challenge. In order to overcome these losses in the fiber, we would need to have long-lived quantum repeaters, which we don't actually know how to build yet. And so in the intermediate regime, we think that going to a free space communication, where the photons are actually distributed through air or through vacuum, will actually help to alleviate this problem of range. So for example, in order to get minus 80 dB of loss in free space communication, we're talking about 400,000 kilometers. So you can see that already the scale at which we can distribute entangled photons is going to be much simpler if you are going to go in free space. And therefore, we think that putting entangled photon transmitters or receivers on satellites and using them to link up fiber networks that's on the ground is going to be of use. Therefore, a quantum network in the future would probably be a hybrid system where you have fiber-based entanglement distribution over a metropolitan region, and then this city-sized networks will then be connected by a free space, either using high altitude platforms or some kind of satellite. And this is where the community is moving towards. Now we restrict ourselves to a discussion about quantum satellites and how they can actually be used to distribute entanglement. Most of the work will fall into these 4 different categories. For convenience, I label them as 1, 2, 3, and 4. And where number 1, we talk about an uplink, where you put a quantum receiver on the satellite, and you can put the entangled photon source on the ground, so that this way you can have a satellite and a ground-based system sharing entanglement. Or you can have a downlink, where you put now the transmitter on the satellite. What we would really like to do is actually to put an entangled photon source on the satellite with 2 telescopes. So you can have a double downlink, and these 2 ground receivers can actually receive entangled photons without having to have a fiber connection. And of course, at the same time, you can augment any of this entanglement distribution techniques by having the satellites also being able to perform inter-satellite communication. And so this is actually quite important for future developments. But at the moment, most of the teams are still trying to demonstrate the technologies in space, and we are all working on different variations of 1, 2, or 3. Now, the Micius satellite, from China, is actually the most interesting platform we have in space at the moment, and it really shows what we can do if we have an entangled photon source in space. And the Micius satellite is really leading the way in building global quantum communication networks by putting an entangled photon source on the satellite and having 2 telescopes on the satellite. They can already do this double downlink approach. And also at the same time, they've done a number of quantum communication primitives like teleportation, decoy state QKD. And I just want to point out that very recently, just last month, they published a recent paper in Nature showing how this double downlink approach can actually allow a very secure entanglement-based quantum key distribution. And if you are interested, I suggest you access this paper and have a look at it. Now, when we talk about how we're going to deploy satellites in space, sometimes we have to think of constellations as well. This is because a single satellite in space doesn't cover the entire surface of the Earth. And typically, when the satellites are near the Earth in what we call a low Earth orbit, like the orbit that the Micius satellite is in, it would actually cover the entire surface of the Earth in 24 hours. And so this means that on any point on the Earth, your revisit time is about, 24 hours. So if you wanted to increase the revisit time, you would probably have to have some kind of constellations. And so one of the things that the community is thinking about is how can we actually get access, to a constellation that's cheaper and faster. And one of the ways we have been thinking about is to use new satellite technology called nano-satellites. And in this picture over here, I'm just giving you an idea of the scale of how the satellites compare. In this picture over here, you see the internals of the Micius satellite as was being assembled. Whereas in this picture over here, you are looking at a 3U CubeSat, okay, which is a stack of three 10-centimeter cubes put together. And this is actually the engineering model for SpooQy-1. And you can actually look at the scale, and this is actually a complete satellite. And so we are thinking that, with nano-satellites, we can actually get access to space more easily because they're smaller, they're easier to launch. And of course, the big challenge is how would you actually package all the necessary instrumentation into the satellite. Now, when we started this, journey back in 2010, and we started to dream about putting, entangled photon systems on nano-satellites, we were thinking originally of using the nano-satellites just to demonstrate key pieces of technology before they are integrated into a larger satellite. However, as we started working on the system, we realized that nano-satellites are not that bad, and that perhaps they could also be used to house a telescope with which you can actually transmit entangled photons down to a ground receiver. And so in this paper here, which was published with colleagues from various universities, we discussed, how a small satellite, for example, a 6U CubeSat, which is made up of 6 units of these 10-centimeter cubes, could actually be assembled into a structure where it would have, the entangled photon pair source and also, telescopes that could actually point accurately to a ground receiver. And so nowadays we are moving slightly from just using the nano-satellites as just a demonstration platform, but also to think about how they can actually be used to actually do the actual communication as well. And this is actually something that various groups have picked up on and are pursuing around the world at the moment. But let's take a step back. Before we can actually do that, we would actually need to demonstrate that we have an entangled photon pair source that can actually operate on this small satellite. And so our development plan, since we started work on this back in 2010, was, to try and do a series of iterative steps. And the first one was just to show that, we could produce, correlated photons on a small satellite in space. And so we actually, tried to build correlated photon pair sources that could fit onto the smallest actual CubeSat. And these sources were very small. They were the size of a sandwich. And we tried to make sure that the interfaces were all standardized, so we can actually work with many different satellite teams. And in the end, we were successful. We managed to launch one of these correlated photon pair sources on the NUS-built Galatia CubeSat in 2015. And after that, we actually got a bit of confidence that our techniques of assembly and that these correlated photon pair sources would actually work in space. And so we started working on converting these correlated photon pairs into an entangled photon pair source, so we could demonstrate full entanglement. And then we actually, built a dedicated satellite, which is SpooQy-1. So this is SpooQy-1. Okay, it was launched in early 2019 to the space station before being deployed in June 2019. And so once that is done, we hope that we could actually work with collaborators to actually try and build, a small satellite, a nano-satellite that could actually, attach the entangled photon pair source to the telescope and to do the full satellite to ground entanglement distribution. And we are working with a team in the UK at RAL Space. This is the Spectre mission, and we are thinking that the satellite at the moment is probably going to be a 12U satellite. So it will be 4 units of this, SpooQy-1 put together. Now, the goal of the SpooQy-1 mission really is just to demonstrate that we have a source of polarization entangled photon pairs in space. At the same time, it will demonstrate some newly developed components. For example, mechanical flexure stages that can actually withstand launch conditions and temperature variations in space, isostatic mechanical mounting systems, and also to try and understand, what is the radiation effects on the components in space. And so that means we want to investigate the aging of this payload as it's orbiting the Earth. Now, the mission overview is actually as follows. We launched in April 17, 2019 to the ISS, where it was, stored for a few months before being pushed out of the space station on 19th of June 2019. And after launch and early operations, we want to establish contact, and we managed to do that very early. Right the next day, we established radio contact, and then we got the first accurate 2-line element describing the orbit of the satellite from NORAD on the 22nd of June. And on 23rd of June, we started doing spacecraft health checks, and we started recording, housekeeping data just to commission the satellite, just to be prepared that we can actually turn it on. And after that, we started going to the science phase. And we have been running the science phase ever since, the 1st of July. And over there, in the science phase, we measure temperature, we measure, the quiescent state of the detectors to look at what is the background rate they're recording. And then we run quantum experiments as well. And we did that all the way until the end of 2019 before we handed over some of the operations to one of our spin-off companies. And we hope to do this for another year. Originally, when we scoped out the mission, we thought that SpooQy-1 would return to the Earth's atmosphere within 12 months and burn up. But at the moment, looking at how the satellite is orbiting the Earth, we think that it will remain in orbit for at least another 12 months. So we would have quite a bit of time to study the science and the aging of the instrument on the satellite. Now, this is a picture of the spacecraft, a cutaway picture. Most of the time, the spacecraft is actually covered in solar panels so that we can charge up the batteries. But essentially, what we have is we have UHF antennas, okay, with which we can communicate and control the spacecraft and the experiment. One section of the satellite is dedicated to satellite avionics, right? And then the other 2 sections is dedicated to the instrument. The quantum payload, we call SPEX2, sits here in this white box, and it is mounted on an isostatic mount assembly, which we co-developed with our colleagues at UNSW in Canberra. And so this is actually what the big picture of the satellite looks like. If you go in and look at the entangled photon pair source, this is an exploded view over here. And from the top, you will see the payload cover, with which we use to ensure that there's light tightness in the instrument. And this is the entangled photon source, where we produce entangled photons and we detect those entangled photons on board the satellite. And we have a little heater, okay, to try and stabilize the temperature, because sometimes it can be a little bit cold on the spacecraft. And then we have a custom electronics board with which we operate all the optoelectronics that we require. And on top of that, we have this isostatic mount assembly, and then a custom structure that interfaces the payload to the satellite. Now, this isostatic mount assembly was actually quite important for us, as you will see later, because we needed a way to minimize the thermal interface between the instrument and the satellite itself. This is because as the satellite orbits the Earth using the ISS orbit, it would be in the sun for about 60 minutes and maybe in the Earth's shadow for about 30 minutes. And this causes a big temperature variation on the surface of the satellite. And what we need to do is make sure that this temperature variation doesn't transfer onto the payload itself. And therefore, this mount was actually quite important. Now, if you were to look at just the optics, there's actually quite a large number of components. But essentially what we have is we have a little blue laser diode that pumps two BBO crystals. And this is where the entangled photon pairs are produced. And then they would then be transmitted down to two single photon detectors over here. And by looking at the correlations between these detectors, we can actually verify whether we have polarization entanglement. Now, in order to address the unique thermal environment that I was describing, we had to design the isostatic mount to control the thermal interfaces between the instrument and the satellite body. But at the same time, within the instrument itself, we had to design certain mounts just to make sure that crystals are held in place without being shaken or made loose during the launch conditions or during the temperature cycles that we expect. So in this picture over here, you're looking at a custom-made mechanical flexure stage made out of titanium, where we would actually mount a crystal over here. And this is actually the region where we actually have the flexing. And so these designs were actually built in-house at CQT, simulated on the computer, and then actually tested in space, just to show that we have both the resolution that we need for tuning the crystal and also showing that it's actually stable or the expected temperature variation. Now, in terms of temperature variation, I've already told you that we expect on a 90-minute cycle, a long day of about 60 minutes and a short night of about 30 minutes. But this is not always the case, because as this satellite were to orbit the Earth, it will also precess around the Earth. And so sometimes it goes into very long days. Okay, and in this picture over here, what you can see is that you can actually model the time in eclipse in terms of minutes, okay, for different parts of the year. So for example, when it was first deployed around June, we expected that the amount of time in eclipse in nighttime for the satellite would be between 34 to 35 minutes. However, due to the precession, very rapidly it would enter a condition that we call the high beta angle, where the satellite would essentially be continuously illuminated. Okay, and the amount of time it spends in the eclipse is essentially zero. And you actually get several of these variations throughout the year, and sometimes you can also get dips. And so this is one of the reasons why we had to spend so much effort in making mechanical mounts that would reduce that thermal interface with the satellite body, because you can imagine that we can design a system that would work with this type of eclipse, but if it was continuously illuminated, the satellite could actually get quite warm. And how would you actually try and reduce the amount of temperature or heat flow into the instrument? And this way those mechanical mounts actually turn out to be very, very helpful. Now let's take a closer look at the entangled photon pair source. The final design of the photon pair source that we came up with is described in this picture over here, where we have two BBO crystals. And so what's happening is that these two BBO crystals have the optical axis parallel to each other, and in between them we have a special wave plate. So what we do is we try to design entangled photons that are emitted at around 800 nanometers. Okay, they're slightly non-degenerate, means that there's on either side of 800 nanometers, so we can separate the signal and either photon according to their color. And we pump this with a blue laser diode that emits at 405 nanometers. So this blue laser light beam would actually walk off inside the crystal. Okay, so it'll enter at one point, but it'll leave at another point. And as it's walking off through the crystal, it will produce photon pairs throughout, its entire journey within the crystal. This means that the photon pairs that you produce would have an elongated output, or like an ellipse. Now, what's happening is that this wave plate would then, rotate the polarization of these photon pairs, okay, so that when it enters the second crystal, it will also undergo a walk-off, just like the pump crystal, the pump photons. Now, this walk-off is an effect of the crystal structure, and it depends on your polarization state. And the reason why we wanted to have this walk-off was so that at the output, the ellipse of the photons from the first crystal would more or less, overlap with the ellipse of the photons from the second crystal. And when you have done that, your spatial mode overlap would be very good, so that after some temporal compensation, no matter where you look on this joint ellipse, you will get very high quality entanglement. And so just by controlling the size of the pinhole, you can actually get a pretty good entangled photon state. And we actually measured the brightness of such a source. Okay, so for example, we had different crystal lengths, okay, for the BBO crystals, and we found that for most of these crystals, you could actually tune up the pump power and also the aperture with which you are collecting the photon pairs, and find that you would typically have between 99 and 96% fidelity to the optimal entangled state, while having up to about 200,000 photon pairs a second for every milliwatt of pump power that you use. And that's actually very good, because at this rate, we have 40 milliwatts of pump power, and we could easily saturate the single photon detectors on the satellite. Now in this slide over here, we are looking at a simplified model where we have the laser diode, which is actually pumping the two BBO crystals that's producing the entangled photons. And then you can look at the path of the SPDC photons, okay? And you can see that we have a little device over here, which is a dichroic mirror that separates the photon pairs according to their color, so that the signal photons will come to detector 1, the idler photons will go to detector 2. And when you detect both photons that come from the same pair, you actually get a coincidence click that we can detect. Now P1 and P2, you can think of them as the polarizers that are in front of the detectors. So by adjusting these polarizers, we can actually look at the polarization correlation between these detectors. And from there, you can make a statement about the polarization entanglement. Now, one of the important things about our design on the satellite was that we didn't put a lens over here. And so most of the SPDC photons, as they were coming out of the system, they would not fall on the active area of the detector. Okay, the reason why we did this is a technicality. We didn't want to put a lens in because we were concentrating on validating some other instruments. So, however, that doesn't really, detract from the fact that we can still demonstrate entanglement correlations in space, because the mode of the signal and idler photons as they were leaving the crystals would still overlap on the detector active area, which is given by this green spot, whereas most of the SPDC photons that we will produce will cover a larger spot over here. Okay, so this is just a technicality to explain how we actually, move the detector such that we can actually always pick up high quality entangled photons. Now, moving more to some engineering aspects, we actually have two ground stations, one in Singapore, okay, and one in Switzerland. They're identical Yagi antennas, and they're linked by internet connection, so that from Singapore we can log into either ground station and communicate with the satellite in space. Now, the main reason why we had two antennas was because of noise. in this map over here, you can see the noise floor of our ground station in Windisch in Switzerland and the noise floor in Singapore. And we sort of expected that the noise floor in Singapore was always going to be worse. For example, typically you would see a lot of noise at least at minus 84 dBm in the channel that we're interested in, whereas the maximum noise that you would see in Switzerland was only minus 103 dBm. Okay, and we already knew about this noise floor in Singapore from our previous work with the Glacier team, where we had lots of challenges in finding time where we could actually talk to the satellite. Now, the reason why it's so noisy is because these small satellites, the radio communications uses something called UHF, and UHF is a very common radio technology that's used by a lot of people, including amateurs. So there's actually a lot of background noise, especially in an urban environment. So we managed to, work with our colleagues at FHNW in Switzerland to set up a very nice and quiet ground station. And so this is just one of the things that we actually have to, take care of as well. Now, when we, set up the ground station and it was validated and we had already assembled the entangled photon phase source and the detectors, we had to go through verification. So typically we will go through both the random vibration testing, which mimics launch conditions, and then we will put it also into a thermal vacuum chamber. This thermal vacuum chamber is available at Singapore Technologies, and they were very nice to give us access. So we can actually put in the SpooQy-1 satellite, both the qualification model and the engineering model, just to see that the instrument and the satellite itself survives the thermal vacuum conditions that we expect in space. So after everything was done, we packaged it, shipped it to Japan for integration, and of course it was deployed. And here's a close-up photo which was taken by another astronaut, and you could almost imagine that if you were to zoom in, you would see the logo of CQT, which is implanted on the satellite itself. So as soon as the satellite was deployed, we had to try and find what were the optimal conditions. And this is actually trickier than it sounds. This is because as you deploy the satellite, one of the things that we have on board is something called a magnetorquer. And the magnetorquer is needed in order to prevent the satellite from spinning out of control. As the satellite is pushed out of the space station, it gets into a kind of spin, and there really is nothing to control that spin. And so if the spin was too fast, for example, two things can happen. Number one, your radio comms may not be optimal. Number two, your solar panels don't get enough illumination time, and they will fail to charge the battery. And if that happens, then the mission's over. So what we had to do was put on this magnetorquer that senses the Earth's magnetic field, and then it would try and slow down the rotation. However, this introduces a complication. When it does this, it is doing this according to its own algorithms, and so it always presents different phases of the satellite to the sun, and this can actually cause small changes in temperature that we don't want. So for example, in one of the orbits that we were studying, we saw that the temperature on the instrument varied between minus 5 degrees Celsius and 10 degrees Celsius. So if you wanted to work with this condition, we would then have to switch on the heater somewhere over here, raise it to about 15 degrees Celsius, and then run the experiment. However, this is not always the case, because from day to day, the amount of time that the satellite spends in the eclipse, this period over here, is varying. At the same time, when it's in the sun, the magnetorquer is causing the satellite to present different phases to the sun and the Earth. So the rate of heating is slightly different. So you could overshoot or undershoot with your heater. So we actually spent quite a few weeks studying this behavior to try and understand this. And we actually spend a lot of time making plots like this, looking at where we expect orbits, where We had eclipse time when we could actually turn on the heater, and we had to spend weeks modeling this before we could actually find what we call the optimal conditions. However, we managed to do that, and our first set of nice curves was obtained in July last year, where we could see this nice polarization correlation curves, and you could actually extract the CH-SH Bell inequality violation from these values. And this is just a comparison against the curves that we saw on the ground. Okay, this is right after the satellite was fully integrated and we turned on the payload. This is the correlation curves. The contrasts are similar, and the brightness is also similar. So this was actually really nice. It was a very nice confirmation of what we could achieve. At the same time, this is the a plot of a bunch of data that we collected between July and December. Okay, and so most of this data over here shows you that we can actually tune the quantum payload to produce high quality entanglement correlations over a range of operating temperatures. And this is possible, okay, because we actually mapped out on the ground what temperature, okay, and what laser current would actually give us a high contrast, okay, a high quality entangled photon state. And by using this lookup table, we could actually decide what was the laser current we would use for a particular orbit, and then confirm that we can achieve entanglement. Now, of all of these plots over here, we have also 3 data points which is in red. And these 3 data points which were in red, just to show you that we managed to also run the experiment and get high quality entanglement after the satellite had gone through its first high beta angle condition. Remember, the high beta angle condition is when the satellite is continuously illuminated. And for us, there was a really dangerous time because we weren't sure whether our isostatic mounts that we had designed and put in place would actually allow the the temperature variation between the instrument and the body to be controlled. But fortunately, it seems like we have very good evidence now that the isostatic mounts work very well, and this is the way to go if we were to build further entangled photon sources for the future. So apart from demonstrating entanglement in space, we also want to understand the aging of the system, and in particular, the aging on the detectors. Now, the aging effects for detectors come primarily from radiation effects. For example, you have charged protons going through the detector, they often damage the silicon, and this damage causes noise to be much more prominent in the detectors. So with sufficient time in space, the detectors will become too noisy to be useful. And so we needed to understand what was the typical rates at which these detectors would accumulate radiation damage, so that in the future we can think of what are the mitigation properties. For example, should we try and cool the detectors down very rapidly? Should we put in some kind of annealing, or should we try and put in some radiation shielding as well? And so in this figure over here, you're looking at data for our detectors from 23 days in orbit and from 269 days in orbit. And as expected, there is an increase. But from a technology perspective, this increase is actually quite manageable. For example, if you look at the 0-degree temperature range for detector 1, we have duck counts on the order of about 5,000 events per second, okay? And after 269 days, we would have about 40,000 events per second. And so typically when we operate with these detectors, we don't operate them at room temperature or even at 0 degrees Celsius, but we operate them much colder, at around -10 or -15 degrees Celsius. And you can actually extrapolate these curves and see that the temperature, the radiation effects are not that bad. And also at this rate, at this amount of radiation damage, we believe that annealing the detectors, warming them up and keeping them warm for about a few hours at 80 degrees Celsius would actually anneal away most of the radiation damage. And we have evidence for this in our labs and also from work done by our colleagues in Canada. For example, Thomas Janowine has some experiments where he shows that by heating up a detector, for example, using a powerful laser pulse, can actually anneal away the radiation damage. And so this is actually good news for us, but we will continue to monitor how this radiation builds up over the next year. So our research, into entanglement technology also is continuing. And one of the nice things about, trying to build everything for a very small satellite in space is that, necessity is the mother of invention. And so the SpooQy Action team has actually been working on quite a number of, possible entangled photon source designs for future applications. We may not always stick to the BBO material. We may also explore periodically pulled materials. And so, for example, in this diagram up here, we have a single KTP crystal where we make use of polarization and momentum conservation across a single pump beam. And by putting in a segmented wave plate in one half of the emission output, you can actually cause the photon pairs that are born in the bottom half to recombine with the photon pairs born in the top half so that you actually can get polarization entanglement. And one of the nice things about this system over here is that it has minimal components and so it's actually very compact. We can also think of more traditional techniques. For example, you can have a beam displacement system. And one of the things that our team is studying with this particular system is how to pump the crystal with a free-running laser diode. Now, most of the time when we do these experiments, even on SpooQy-1, we use a laser diode with a very well-defined wavelength, with a bandwidth that's only a few hundred megahertz. But one of the things we've been thinking of doing is trying to increase the pump power. And the nice thing about using a free-running laser diode where the bandwidth is in the gigahertz is that they can easily go up to hundreds of milliwatt. And what we have found in this particular design is that by adding an additional pre-compensation crystal over here, we could actually pump the whole system with a free-running laser diode and actually achieve really high brightness. For example, we are talking about 500,000 pairs of observed entangled photons for a single milliwatt of pump power. And when you have over 100 milliwatts, you're talking about really bright sources. Now, I want to just, conclude by saying a few words about what we can look forward to in the next 5 years. So in June this year, it was actually a very good year for quantum technologies in space because we had 3 very nice papers that came out. Of course, there was the paper that we published on SpooQy-1. There was also the paper from our Chinese colleagues where they showed that the double downlink experiment could conclusively be used to demonstrate quantum key distribution. But at the same time, our colleagues in the US also published a paper where they demonstrated a Bose-Einstein condensate on the International Space Station. And so that's actually very unique because if you could actually put a BEC into space, we're talking about possible applications in the future for quantum memories or quantum repeaters based on atomic systems. So that's actually very nice. And I also understand that in the next few years, there's a US-German collaboration called BACAL that's actually under active development at the moment. And also on the space station is also going to host some of the advanced atomic clock systems. So for atomic-based experiments, we can look forward to some very interesting times in the next 5 years. Now, for quantum communications, we have a number of CubeSat-based missions that's going to come up. Of course, there's our Spectre mission between NUS and RALSpace, but also our colleagues in Germany have a system called Cube, which is designed to demonstrate quantum communications from a 3U CubeSat, if I'm not mistaken. And another group of UK colleagues have a CubeSat mission called ROX. And this is the ROX concept, as you can see over here. And of course, we also have larger spacecraft that is being planned. Thomas Janowine in Canada is now working actively on building the KeySat mission, which is an uplink mission. So it's very different from this downlink approach. What we would do in an uplink approach is we would have all the transmitters on the ground, and we would have a satellite with just the single photon detectors. And this is something that we can look forward to in the next 2 or 3 years. Our Chinese colleagues are talking about launching various types of spacecraft to investigate smaller platforms. And also, one of the things that I'm really looking forward to is a Micius follow-on that's going to be launched at a very high altitude of 10,000 kilometers. Now, going to high altitudes is actually very exciting. This is because it would alleviate some of the challenges that we have in tracking these low Earth orbit satellites. When you're talking about low Earth orbit, for example, Micius or SpooQy-1 or any of this CubeSat spacecraft, they are about 500 kilometers above the Earth. And so if they were going over your ground station, they would complete a single pass in about 5 to 6 minutes. This means that your ground-based receiver has a very short time to collect any signal. And so your tracking has to be actually very good. And it's also kind of expensive because you must slew at a relatively high rate. If you're at a very high altitude, like what our Chinese colleagues are proposing, then you can actually slew at a much slower rate, and so you can increase the time with which you can collect signals. And our European colleagues also have big spacecraft programs that's coming up, QKD-SAT and Quartz, which I think will also launch in the next 2 or 3 years. So it's an exciting time ahead. And beyond the next 5 years, we can think of, beyond direct communications. We can think of how we can have memory-assisted, quantum communications in space. And, we're already thinking of various designs. For example, in this particular design over here, which was a proposal that just appeared in the archive, our colleagues were thinking of how they could actually put the Bell state measurement devices also in space and not just on the ground. And so this is where having inter-satellite links become very useful. And the main reason why they wanted to put this in space was that if you were to transfer signals, from entangled photon sources directly, mostly through space, then the amount of transference is higher, the transparency is much higher, because you don't always have to go to the Earth's atmosphere, which can introduce losses. And so, beyond 5 years, we are looking at, more advanced experiments, and hopefully we begin to see some of these memory-assisted experiments being deployed. And so with this, I just want to, thank all the people that have been working on the SpooQy project. This would not have been possible if the talent wasn't here at CQT. So at the moment, these folks, Tanvir, Aisha, Chitra, and Subhash, they're continuing to work on the SpooQy project and on the Spectre project. And some of the past members who have been working on and contributing to the SpooQy-1 project are listed here. Some of them, like Alex, Huai, Marie, Tom, and Rob, they've already joined Spectral, which is a spin-off company. And in the SpooQy-1 project, 3 PhD students contributed tremendously to the development of that entangled photon pair source. This is Tongkan, Rakita, and Aitor. And you can see that the 3 of them are posing for a photo with the entangled photon pulsars. I should also say that ITO has joined our spin-off company as well. I need to thank our collaborators, Daniel. So Daniel and I first came out with this idea of using nano-satellites in 2010. Christoph really helped us, with some of our very early experiments with balloons, high altitude balloons, and also Christoph is responsible for our Swiss ground station. And Douglas Griffin in Australia, who helped us, scope out the design for the isostatic mount. And also, last but not least, space missions are complicated, they take a long time, and we often have external reviewers acting as advisors. And the three reviewers that we should thank are, again, Doug, but also Alan Smith at UCL, MSSL, and Hans Kuiper at TU Delft. And so with this, I would like to end my talk. I would like to thank you for taking the time to attend and to listen to what I had to say. And I hope you will continue to tune in the future to see what we're up to with Spectre and with more advanced projects. So thank you again for your attention, and I think we will have time to take some questions.